Well, good afternoon. This should be Cal 3 class. It's 12:20 in the afternoon. The class was supposed to start at 12:15. I was running a little late because I was trying to finish my salad, but I didn't get a chance to. Had a student, had questions and took up too much of my time. But anyway, I got a little bit to eat. So I thought I was running late, and I was a little bit, but nobody else is in the room. So I'll go on and get started with today's class. Well, where did it go? There it goes. We'll start from current slide. We are recording, so let's go. I was going to ask if there are any questions, but there's no one here to ask. So I do want to give you some piece of information before we get started. I finally heard back from the guy at Cengage with a course code, and here is the course code for this class. Now, you don't have to use it, but if you did choose to go through Cengage Unlimited, to get your books, and you need access to the ebook, or you want to use WebAssign or any other thing like that, here is the code for the book. For this course. It's called the class code, if that's what they ask you for. It always starts with Lawson, Lawson, .al, space 3668, space 8058, 8058, okay? And when folks come in, I'll go back to this again. So the course code for this course, Cal 3, is Lawson.al space 3668 space 8058. Okay? And right now, I'm the only one in the room. Okay. Now, my memory is that where we left off last time was at the top of page 788. Chapter 11, Vectors and Geometry of Space, 11.5, Lines and Planes in Space. And we had done example 1, and that's what's on the screen now. They skipped example 2 in the text, in the slide set. But in the text, you'll see that example 2 is C. LarsonCalculus.com for an interactive version of this type of an example. So if you want to go there, good place to go. Okay? Now, I'm going to write on this slide because they don't have a slide for this example. So let me write it here. Find a set of parametric equations of the line that passes through these 2 points. Here's the first point, -2, 1, 0, and 1, 3, 5. Sorry, crowded there. Okay, we need a set of parametric equations for the line that passes through those 2 points. Okay? Well, one sort of, I hope, obvious first choice would be find the vector between those 2 points. That would be make sense, wouldn't it? So let's find the vector, and I think they name it V, so let's call it V. Vector V between these 2 points, and that vector would be, I'm going to choose this as my initial point, that's terminal. It really doesn't matter, it goes either way. So 1 minus a minus 2 would be a 3. 3 minus 1 is 2, and 5 minus 0 would be 5. So there's the vector between those 2 points. Okay? Yeah, 3, 2, 5. Okay, I was going to say, woo, where is it? There it is. All right, there's the vector between the 2 points. Now, if you recall from before, once you have that vector, then you can use either one of the points to be your, sort of the reference point, okay? So maybe to go back and give you a little bit of a an idea of the parametric equations. That's what they're asking for. Find the set of parametric equations of the line that passes through those 2 points. We've got the vector, and remember they said a line parallel to that vector that passes through any point, either one of those two, and they happen to choose the first point, which is fine to choose. There's nothing wrong with it. Then to write the parametric equations, all you do is x, that's going to be your parametric equation for x, is going to be x equal, and you can do it either way. I'll do it the way they did in the book, minus 2 plus 3t, or any other parameter you might want to choose. Their favorite is t. Y is equal to 1 plus 2t, and z is equal to 5t. Okay? The point -2, 1, and 0 came from the point. Okay, that's where those values came from. The 3t, 2t, and 5t comes from there. So there's the equation. It's pretty straightforward, simple to write. This is 1, -2, x equal -2 plus 3t, y is equal to 1 plus 2t, and c is equal to 5t. Okay, as t varies over all real numbers of parametric equations, determine the points on the line. Now, if you set t equal to 0, you get the first point right there. -2, 1, 0. Okay? If you set t equal, hey, I'm glad to see somebody. I get sort of wacko talking to myself, so I'm glad you're here. Okay. That's Muhammad. Okay. And today's the 29th. What's that?
I was running late. I was worried I was going to miss it.
Yeah, I was running a little late because I had a student stop after the last class and talk for a while, so I didn't have much time. I usually try to eat my salad between classes. I didn't have time to finish my salad. I was cramming as I got to go. And I had to stop by the restroom and rinse my hands off because they were sticky from the salad. But I was late getting here, and I was the only one in the room. So let me get set up here. I've already started on the example that we were at. Lights here. So you'll be able to see. Now, this is the second time this has happened today. No, it's doing something. I press the button and nothing happens. Here it comes. Now. What's that?
I was running here, but I left my pen in the car.
Left what?
I left my utensil in the car.
Okay. There's a few up here. I don't know. You rather have pencil or pen? Pen? Okay. Try it and see if that works. That's just one that was left in the classroom. It does. Okay. All right. First, before we get started, I did finally get word from the guy at Cengage. There's our class code. If you need to do ebook, WebAssign, any of the things that would be available from Cengage, that's the class code you'll need. Lawson.al space 3668 space 8058. Okay? Lawson.al space 3668 space 8058. Now, I don't know how important the spaces are or not. That's what he gave me, so that's how I wrote it down. Okay. Maybe you don't need the spaces, or maybe you do. Okay. Now, where we were supposed to begin today was in Chapter 11, Vectors and Geometry of Space, 11.5 Lines and Planes in Space, and we were on page 788 at example 2, parametric equations of a line through 2 points. And that's what I did here. It's not on the slide set, so I did it. Here are the 2 points, negative 2, 1, 0, and 1, 3, 5. Those are 2 points. Now, to get the parametric equations, that's what it said, a set of parametric equations for the line passing through those 2 points. And here's Jeremy. Good to see. All right. Again, let me start over again. I finally heard back from the guy at Cengage, and he gave me the class code for this course, for this class, and it's Lawson.al. That's how all of them start for our school, Lawson.al, space 3668, space 8058. I don't know if you use WebAssign, if you've got a book, you may not use an ebook, you didn't get on Cengage Unlimited, okay. So you probably don't need it. But if you want to use it, it's there. Now, I gripe and complain and fuss about WebAssign all the time, but they do have good tutorial help. You know, it is a good package for that.
But not personal help.
It's what?
They're not good in, it's like one-on-one assistant.
I don't know. I've never used them.
I tried. But
You've tried, they're not. Okay.
You're going to wait an hour, like, for just one problem. And then
Really?
move on to the next person. I was like, waiting for 1 hour. Yeah, I can only have one question. That's not
Okay. I didn't know that, but it's good to know. I do know that a student came in this morning, after the first class this morning, and she stopped by afterwards and said, help me with this problem. I said, you want me to put it on this? He said, no. So she wrote it on the board. And I can't reproduce it exactly. I could if I thought about it for a while, but it had fractions in it. And the first term was the x squared term, and here was a 1/3 x squared, and then the other one had a 2/3 x squared. And then the second term was the linear term, and I don't remember what it was. It was plus 1/2 x, and over there it had a plus 1/2 x. And then this had a minus 3/8, and over there it had a minus 5/8. So you add those together, and it was supposed to add these two together, add them together. These two added to be x squared, the next one added to be x, and the next one added to be minus 1. It was pretty straightforward. And she said, yep, but they kept telling me that's the wrong answer. And it's absolutely correct.
Yeah,
and
sometimes the input, they have a specific way they want you to input it.
Yes, but that one, I couldn't think of any other way to write it, except x squared plus x minus 1. I guess you could have written all with fractions in there, but...
Well, the best way to do is, like, you can go to the examples
yeah.
and see how they wrote there and find
Yeah.
how they wrote there.
Yeah.
Just, even if it might be wrong way they wrote it, but you just duplicate exactly what they did.
Yeah. But, the only other way could have been 3/3 x squared plus 2/2 x is minus 8/8. But who would write it that way? Nobody, so I don't know. Anyway, I'll get off of that. So anyway, first thing to do then, I thought I saw you here earlier. Okay. This is Christina, right?
Yes.
Okay. There you are. Okay. Now, as I was telling the others, I'll say every time someone new comes in, I did finally get a class code from the guy at Cengage. And here it is, Lawson.al, Lawson.al, and then he had a space, 3668, and then another space, 8058. Now, I don't know how important the spaces are, but what he sent me, that's how it was written. So that's how I wrote it. And where we left off last time was chapter 11, which is vectors in the geometry of space, 11.5 lines and planes in space, and we were on example 2, which they didn't have on the slide set, so I did it here. It said find the parametric equations, a set of parametric equations for the line that passes between these 2 points. Okay? So, you write down the 2 points, negative 2, 1, 0, 1, 3, 5. Okay? Now, first, easiest, best thing to do, come up with a vector between those 2 points. Okay? And that's pretty easy to do. Choose one of them to be the initial point, one the terminal point, and do the subtraction. I chose this to be terminal, so 1 minus a minus 2 is 3. 3 minus 1 is 5, and 5 minus 0, 3 minus 1 is 2, and 5 minus 0 is 5. So there's the vector between those 2 points. Okay? Now that vector could be anywhere in the space, but it's always going to be that orientation. So now you got the vector, use either one of the points. It doesn't matter which one you choose. I chose the first one, the book did too. Easy to use. And then the x value is the x component from here plus 3 times your parameter. And the 3 is the component of your vector in the x direction. The y value would then be the y value here. Y is equal to 1 plus 2 times t. Now, you don't usually use t. You could use s, any parameter you want to use. I wouldn't use x, y, or z, obviously. I probably wouldn't use v because we're using that in the problem. But any parameter would be a, b, c, whatever. Anything other than something you already used. And then the z parameter would be 0, which don't put anything down, plus 5t. Now, that is a set of parametric equations that represents the line that goes between these 2 points. And lo and behold, I believe I've recognized this guy. Okay? It is Terrell, and I'll even mark you present. I feel generous today. Okay? Now, let me start back over again. I finally heard from the guy at Cengage. There's the class code for the course. I don't know if you need it or not, but if you want to use WebAssign, he put some problems out there. I'm sure they're fine. I just don't care for WebAssign, but I had to have it in order for people to access the ebook if you were going through Cengage Unlimited. I don't know if you did. You probably already had the book and don't want to mess with it, but you got it now. You can use WebAssign anything you want to. WebAssign does have some good tutorial guides in it, but I heard from Muhammad their one-on-one tutorial pretty much stinks because you sometimes have to wait hours to get answered to one little question. So you might not want to use that, or choose your time when you don't think anyone else will be out there. I don't know. But anyway, I hadn't heard that before. But anyway, here is the code, Lawson.al. And they had a space, when he sent it to me, he had a space 3668, and then he had another space 8058.
So the Cengage is on WebAssign as well.
What's that?
So the Cengage is WebAssign. So it is WebAssign?
Do I use it?
Like we have like the Cengage part is not a different website, it's WebAssign itself.
Right, yeah, this is the code that gets you the WebAssign or the ebook or whatever you want. If you're on to Cengage Unlimited. If you didn't go through that, this won't do you any good. I don't think. Because you have to have some sort of code that comes on your stuff that came with your book. You have to enter that and the class code. So if you...
If you WebAssign, usually you can pay it online.
Yeah, you have to have these. So I think WebAssign is something different though from the Cengage. I think you got to have 2 different access codes to both of them.
Okay. If you bought your book... Say again?
With Cengage Unlimited, everything that's connected to that class is included.
Right.
So WebAssign is included.
WebAssign is
Everything
included.
is unlimited access to whatever you have. So we go in, like, my biology class is on there, so when I go and add that, I have access to my biology class and this one.
Yeah. But you need a class code, and this is the class code for this class. There's another class code for biology. It starts Lawson AL, not AL, I bet, but then it has other digits. Okay. Now, with Cengage Unlimited, once you use this, you have access to an ebook, you have access to WebAssign, you have access to everything they've got. But that's only, you also had to buy you got some sort of code when you did it, didn't you?
It might have been part of the text that made the book.
Well, but you don't have to buy the text. So, but didn't when you did? I say I've never done. I don't need to do Cengage Unlimited. When you paid for that, did they give you? Yeah, your receipt has some sort of code on it. And didn't you have to enter that code somewhere?
No.
You did.
Because you go through, you have, before you can get to pay for it, you have to enter all your information to put your classes.
Oh, really?
She, my biology sent us a link that we clicked on. It took us directly to her book and all that stuff. So it's like once I can go in there and register another class and it's asking for a code. So when I go and put in that code, it just pull up my information right there. And then, I can choose. I can get it. Well, I've already paid, so it just pull up.
Okay. What's your major, by the way, that you're taking biology and calculus?
It's chemical engineering.
Guess what?
Chemical engineering.
Okay, and you needed biology?
Biology, one.
Really? I never would have guessed that. Okay.
I'm a transit student from the University of Alabama.
Okay, maybe they require it.
Yes, he had this. It's on my too. But I talked to them. They said really don't need it. It's just people like the person who's making them here made a mistake and I done, and they said they can talk to them.
No, I need it for to transfer back. Yes, but I don't need it for here. Like to go to for my degree, I have to have it.
All right,
It's
Justin,
just a basic.
just in case you need it, I don't know, did you do Cengage Unlimited? No. Are you needing WebAssign or anything like that? Okay. Well, if you ever need it, there's the code. Lawson.al space 3668 space 8058. Okay. All right, we finally got everybody here that's enrolled in the course except Dan, and Dan is trying to do it via, the YouTubes, and so he's heard this several times if he's listening. Sorry about that, Dan. Okay, and the rest of you, Mohammed's heard it every time someone's come in. So there's the code, and the example 2 was where we started on page 788, chapter 11, vectors and geometry of space, 11.5, lines and planes in space. Here was the problem. Write parametric equations for the line that goes between these 2 points. Okay? First step, get the vector between the 2 points. So choose either one of them to be initial and final. I chose that to be final, this to be initial. So 1 minus the minus 2 is 3. There's the x component. 3 minus 1 is 2. There's the y component. 5 minus 0 is 5. That's the z component. So that is the vector that goes between those. These provide the coefficients for your parameters. Pick either one of these 2 points and use and that becomes the starting point, you might say. -2, the x equal, here's your parametric equation in x. X equal -2 plus 3 times whatever parameter you choose. Everybody's favorite seems to be t. You could have used s, a, m, anything. I wouldn't use x, y, or z. That would be confusing. Probably wouldn't use v. That might be confusing. Any other parameter would be fine. Okay? The parametric equation for y would be y is equal to 1 plus 2 times that parameter, t, or whatever. And the z parametric equation would be 0, so you don't have to write anything down, plus 5. Okay. Now, just to convince yourself that indeed these points are on the line described by that, let's see if they are. Well, very simple. Put t equals 0, and you get -2 for x, 1 for y, and 0 for z. -2, 1, 0. That point is there, right there. Okay? How'd you get to the next point? Well, it happens to be if you put in a 1 for t. Okay? Put in 1 for t, and you get 3 minus 2 is 1. 2 plus 1 is 3. And 5 times 1 is 5. Yep, both of those points are on there. These parametric equations work. Okay? That was just a check. You don't have to check it, but if you were doubtful, check and see, and they do work. All right, that's example 2. And by the way, and here's why I don't see why anyone using this text would ever need WebAssign, but you can use it if you want to. And the guy did put some problems out there. If you want to use it, you can. But you see this text, for example 2, see larsoncalculus.com for an interactive version of that type of example. Okay? So even without anything, there's a free website you can go to. You don't need a class code or anything else. Just go to larsoncalculus.com and find this problem, and you'll see an interactive example. And then we'll talk about the others later. I've already talked about them. So let's move on. So the next topic here is planes in space, middle of page 788. Okay? Now, consider a plane containing the point x1, y1, z1. Okay? Now the thing is, there's an infinite number of planes that contain that point. Okay? If this is the point right here, you could have a plane like this, a plane like this, a plane like that, a plane like that. I mean, just any kind of planes that contain that point. So let's just consider a plane that does contain that point. And it has a non-zero, thank goodness, normal vector n, which is ABC. Now what does it mean, normal? Perpendicular to, orthogonal to, at right angles of, okay? That's his normal vector, ABC. They like those 3 letters, don't they? Shown in this figure. So once you have the point, like I said, there's an infinite number of planes that go through that, but once you have that normal vector, that defines one and only one plane that goes through that point, okay? If it has that normal vector, that's the one and only one plane that goes through that point, okay? That plane consists of all the points Q. Q could be any x, y, and z, okay, that is on that plane, for which the vector PQ is perpendicular or orthogonal to n. Okay? Well, that statement right there tells you a lot. You already have the point, and you have this, the given point P, and then you have this variable point Q, and you know that, and you were given the vector n, the normal vector n. So if you know that they're perpendicular, then n dot PQ has to be 0. So that gives you an equation right there. The n is this vector ABC. Okay. The PQ would be, this is the initial point, there's the terminal point, x minus x1, y minus y1, z minus z1. There would be the vector PQ. So you dot this with x minus x1, y minus y1, z minus z1, set it equal to 0. Okay? Well, dot product is multiplying the first component, adding to that the product of the second component, adding to that the product of the third component. So that gives you a times x minus x1 plus b times y minus y1 plus c times z minus z1 is equal to 0. Now, the third equation of the plane, this equation, I guess, is what they talked about. 1, 2, 3. Third equation is said to be in standard form. Okay? Now, just to give you an idea, remember the line? If you had that vector that was in the same direction of the line, that became your coefficients of your parametric equation. And then the point became the constants for those parametric equations. Okay? Well, let's look at what we have here. If you have the normal vector to the plane, that becomes the coefficients of your equation, okay, and in standard form, and then your components of your generic vector that's in the plane, x minus x1, y minus, that becomes the second part. So not quite the same thing, but there are some similarities, okay? So there is your standard form for that. So if you know the vector that's normal to it, in any point on the thing, you can write your equation. And that's not a set of equations, that's one single equation in x, y, and z. Okay? So here's the theorem that states what we just said. The plane containing this point x1, y1, z1, having a normal vector of a, b, and c, can be represented by the standard form of an equation of a plane, a times x minus x1 plus b times y minus y1 plus c times z minus z1 is equal to 0, because that they're orthogonal, these two vectors are. And this is your normal vector, the components of it, and this is your representative of some vector in the plane. By regrouping the terms, you get the general form. That's the standard equation. Here's the general form. Okay? What you do here is multiply through, distribute through. AX minus AX1. Now, these are just numbers, so that gives you a number. Plus BY times the number, that's B times Y1. Plus CZ plus whatever number C times Z1 is. And add the three numbers together, that gives you a D. So you have AX plus BY plus CZ plus whatever the sum of those three products were. That's your D. That's equal to 0. And actually, another way you'll see this sometime is AX plus BY plus CZ is equal to minus D. That's on the other side. You can write it that way. Okay? Given the general form of an equation of a plane, it's easy to find the normal vector to the plane. If you're given that there, here's a normal vector, A, B, C. I mean, it's the coefficients of your three variables. What's that? What was that? D, that just is the result of these numbers here, that one point that you happen to choose. Okay? Choose another point, you get another Z, but the normal vector is still going to be the same. Okay? Now, so let's think back. If you have an equation, two variables, AX plus BY is equal to C, that's an equation of a line, right? AX plus BY plus CZ is equal to D, that's now the equation of a plane. Okay, so same type deal. So here's example 3, using what we just did. Find the general equation of the plane containing these points. Okay? The general equation of a plane containing these 3 points. Okay? Now, wait a minute. The formulas we just had 1 point and a normal vector. We don't have a normal vector here. How could we get a normal vector? Second? How? How do we get a vector normal to two other vectors? The cross product. Remember? That always produces a vector, and it's normal to the two vectors you put in. So, let's pick any two of them. It really doesn't matter, just any two of them, and do a cross product. Okay? Well, let's see. Let me take that back for a moment here. You need a point in the plane. We got 3 points in the plane, so any one of them would work. Okay? 3 choices for that point, but no normal vector. To obtain the normal vector, use the cross product of the vectors u and v extending from the point 2, 1, 1 to the points 1, 4, 1 and negative 2, 0, 4. Okay? So what we do, we pick one of these, and it doesn't matter which one. They chose this one. Okay? Now, that gives you the point, your x1, y1, z1. Okay? Now, here's the two vectors that you cross. You need vectors. Okay? Let's take the first vector would be using this as the starting point, use that as the end point. Get out of there. Okay. And that would be the vector -1, 3, 0. Right? 1 minus 2 is -1. 4 minus 1 is 3. 1 minus 1 is 0. And another vector would be from this point to that point. And that would be a -2 minus 2, which would be -4. 0 minus 1 is -1. And 4 minus 1 is 3. So there's another vector. So here's a vector from this point to one of those, and that point to another. Okay? So now we got two vectors. Do the cross product of those two. How do you do the cross product? Remind me. We're going to call this U and V. Okay, and say again. Okay, you put the I, J, K at the top. These are unit vectors. -1, 3, 0, -4, -1, 3. Okay? And the easy thing to me is to repeat the two columns, first two columns. I, -1, -4, and J, 3, -1. And then do your diagonals. And this would produce 9i, right? 0j plus k. I should be putting those as unit vectors. Now do your up diagonals. And I think just so it'll be easier to read, I'll erase those three down diagonals and do the up diagonals. And these will be minus these. And what would that be? Plus 12 what? K, 0, plus 3. Plus 3 what? J. Okay. Add those together and you get 9i plus 3j plus 13k. Okay. Now you can either leave it like that or you can write it in vector notation 9, 3, 13. Because that's how they did the others. Okay. Now it's a fairly simple process to write the equation of the plane. That's what they asked for. Finding an equation in standard form and in general form. So the standard form is going to be what? Standard form, use these as your coefficients. 9 times x minus x plus 1, x minus or minus 1. Because remember, oh, I'm sorry. Using the wrong thing. Okay, sorry. Here is your point that you're using, right? So x minus 2 plus 3 times x minus 1, y minus 1. I can't write. Can't talk. I can't do anything. Right. Okay, y minus 1 plus 13 times z minus 1. You put x, x, y, z. Okay, these are the coefficients. X, y, z's are there. Minus 2, minus 1, minus, okay. That, and that's equal to 0 because this is your normal vector. This is your any old vector that's on in the thing in generic form with x, y, and z in it. In the plane, and they've got to be perpendicular to each other, so the dot product's got to be 0. So that's your. Wait a minute. Boy, they don't write the same. Okay, sorry about this. Look at that. In the book, it says find an equation in standard form and in general form of the equation of the plane containing those points, and they are the same points, aren't they? Yeah. Where this just says the general equation. So your book says one thing, the slide says another. This is your standard form, which the book asks for. Okay? Now, the general form, which the book and this asks for, you just multiply through it. And what does that give you? 9x minus 18 plus 3y minus 3, 13z minus 13, and that's equal to 0. Well, separate out the variable parts, 9x plus 3y plus 13z, and then combine these, and that's going to be minus 31, and 3 is minus 34 is equal to 0. That's the general equation, okay? Which is all this one was asking for, but the book asked for both of them. Now, frankly, I just prefer to write this 9x plus 3y plus 13z is equal to 34. Let's move it to the other side. But they don't, they like to have it on this side. It doesn't really matter. Same equation. All right? That's how we did it. Let's see how. I hope I did it right. Minus 18 and minus 13 and minus 31. Minus 3 is minus 34.
I canceled the 13 because I forgot that I ignored the z. I was minus 13 and 13. That canceled out.
Here?
Yeah,
Not like terms. Add the constants. And that's what you got. Okay. Let's see what they got. Let's erase those. And to apply that, you need a point. You got 3. Choose one. Doesn't matter which one. Okay? And a vector normal to the plane. So choose a point. Okay? And they happen to choose the 2, 1, 1. Okay? Now, it would have worked okay to choose any of the others. Okay? But once you choose 2, 1, 1, that is your point. And then you need to get a vector to that one and that one. And let's see which one. Yeah, we did. We said U was to this one and V was to that one. From this is your initial point. Okay? And that gives you a U and a V. And that was pretty straightforward to do. Just use the components there. 1 minus 2 is minus 1. 4 minus 1 is 3. 1 minus 1 is 0. So there's the U vector. The V vector is minus 2 minus 2 is minus 4. 0 minus 1 is minus 1. 4 minus 1 is 3. There's your next vector. Okay? That gives you those two vectors. Negative 1, 3, 0, and negative 4, negative 1, 3, just like I said. And then what you do is cross those two vectors. And when you do the cross product, you get that, okay? And they don't show you how you got it. They just said, there's the answer, okay? 9i plus 3j plus 13k. Okay, exactly what we got. And that's your ABC. It's as simple as ABC. 1, 2, 3. Okay. Using the direction numbers for n, okay, those are your direction numbers. And the point x1, y1, z1 is the one you chose, 2, 1, 1. you can determine an equation for the plane in standard form to be a times x minus x1 plus b times y minus y1 plus c times z minus c1 is equal to 0. So basically, what you have then is 9 times x minus 2 plus 3 times x minus 1. What's that?
We started with these that ended up with it.
Yeah.
The first one we did.
Yeah, these are the point you chose to begin with. That's your x1, y1, c1. And what you calculated after you did your cross product, that's your a, b, and c. So you just pull those numbers, 9, 2, 3, 1, 13, 1. You just put those in, there's your equation. Just a plug and chug. So it's 9 times x minus 2 plus 3 times x minus 1 plus 13 times x minus z minus 1. Okay. And then you regroup them. Okay. That's your standard form. And then it says regrouping them. In other words, get all your variables first. 9x plus 3y plus 13z. And then group those three together, and you get minus 34 is equal to 0. That's your general form. General form, a lot more concise, but you sort of see more information with the standard form. All right. Sorry, my head's sort of clogging up on me. I'm having trouble breathing. So, two distinct planes in 3 space can have two characteristics. Number one, they can be parallel to each other and therefore never intersect. Or, if they don't, they intersect and form a line. So, two planes that intersect, you can determine the angle. Sorry. That angle we always use an acute angle, the smaller angle between the two planes. Of course, if this plane continued here, that one there, there'd be a big wide angle here, obtuse angle. Don't use that. Use the acute angle. Okay. Between them, from the angle between the normal vectors. So basically, if you have the two distinctly different planes, you know what their normal vectors are. If you know those, take the coefficients of your x, y, and z. That's your normal vector for the first plane. Do the same for the second plane, and then determine the angle in between those two vectors. That's going to be the same as the angle between the two planes. Okay? Well, how do we get the angle between those two vectors? Specifically, if vectors n1 and n2 are normal to two intersecting planes, then the angle theta between the normal vectors is equal to the angle between the two planes. Okay? And here's how you get that. The cosine of that angle is the absolute value of the dot product. Remember, a dot product may be negative. May be negative. Since you want the acute angle, you always want the positive of that. If this numerator was negative, that's going to give you an obtuse angle because cosine is negative in the second quadrant, positive in the first quadrant. So that's why you take the absolute value of the dot product of those two vectors, divide that by the product of the magnitude of those two vectors. So this is just going to give you a number, and this number, that number, that should be a number less than 1. Why do I say that? This dot product, magnitude of that, or absolute value of that, divided by the product of these two, why do I say it should give you a value less than 1? Because the cosine is always between minus 1 and 1, and if you make this an absolute value, these are obviously linked, so those are positive, then you have something between 0 and 1. Okay? So, consequently, two planes with normal vectors n1 and n2 are perpendicular when that dot product is 0. So that would give you a theta of 90 degrees, where is cosine the first quadrant equal to 0? That's at pi halves. They're parallel when n1 is a scalar multiple of n2. Okay? In other words, when you do those normal vectors and you find out their the dot product is when you do see that the n1 and n2, you just look at them and see that one's a multiple of the other. That means that their normal vectors are the same vector. Okay, they're just magnitude different, but they're in the same direction. That means that the two points are parallel. Okay, let's see if we can see some examples. That was the bottom of page 789. Okay, they didn't do an example. Example 4 is what we need to do. So let's do example 4. We'll do it here. Goodness, I'm having trouble clearing my throat. And I think this happened last time too. I believe part of the issue is, like I was telling Muhammad when he came in, I only got part of my salad eaten today, though it was most of it. But there's very few calories in the salad, okay? And my head is saying, we need something to go on. And I think that's what's going on here. I probably should have eaten a little bit of protein or carbohydrate or something, but I didn't, sorry. All right, here's example 4. Find the angle between the two planes. Here's one plane. X minus 2y plus z is equal to 0. And the second plane is 2x plus 3y minus 2z is equal to 0. Okay? We want to find the angle between those two planes. Now, time out a moment here. What does it mean that we don't have a constant here or here? What does that mean? How did we get those constants? Remember, it would have been 1 times your x1 minus 2 times your x2, y2, and plus 1 times your z, z3, the z value, z1, okay? But that adds to 0, okay? So what does that mean? That initial point is 0, 0, 0 for both of these. In other words, both of these go through the origin. Is that what you said? Yeah, good deal. I couldn't hear. I heard you say something. I meant to ask what it was. But the other way to do it is just look at this, okay? Take a look at it. Can you name me a point that's on this plane? Just looking at it. 0, 0, 0. Right? And this one, 0, 0, 0. Obviously, that's a point on both planes. So we know one point in common, and the line must have that point on it too. Okay? So how are we going to get the angle between those? What was our formula? Cosine of theta is equal to absolute value of n1 dot n2 divided by magnitude of n1 times the magnitude of n2. Okay? Well, wait a minute. What is n? If this is line 1, what is n1? It's a vector, right? And what is it? 1, negative 2, 1, And what's your N2? 2, 3, negative 2. Okay, time out just a moment here. One thing we need to ask ourselves before we even get started is, are these parallel with each other? In other words, is N2 a multiple of N1 or vice versa? And the answer is no. Okay? The only way it could be, for that to be a multiple, 2 is 2 times 1, but 3 is not 2 times negative 2. So as soon as you see that one's not a multiple of the other, you know they can't be parallel. So these are going to cross somewhere. So now let's do the math. Okay? And it's pretty easy to do too. What is the dot product of N1 times N dot N2? That's pretty easy. Dot product, remember that? Long time ago? X component times X component. That would be 2 Y component times Y component minus 6, and Z component times Z component minus 2, okay, divided by, we need to get the magnitude of of N1. Remember what that is? Magnitudes are always square root. Square root of what? One squared is 1. Negative 2 squared is 4. 1 squared is 1. So that's the square root of 6. Right? Magnitude of N1. Magnitude of N2 is what? The square root of? A little louder. 4 plus 9 plus what? 4, isn't it? Yeah, 4. Okay. So that would be 8 plus 9. That's the square root of 17, one of my favorite numbers. Ew. Okay. I just made that up. Okay. Now, so the product of those two is the square root of 102. Is that right? 6 times 7 is 42. Yeah, I believe that's right. Okay. And the say again? And the numerator is 6. All right. You're going to need some calculator help now. I could do just about all this up to this point in my head. Not anymore. Do 6 divided by the square root of 102. That would be something a little bit greater than 10. And then do theta is equal to the inverse cosine of that. And again, use your calculator.
Would it be 0.5?
It has some more decimals.
Yeah, 9.
409. Yeah, okay. And then do the inverse cosine of that number. Yeah, they got, in the book they got 0.5940. Oh, okay, you're in radians. Is that what you said? Okay, what you call it, 0.9? Okay, that sounds right. In our book, for some reason, they did degrees, okay? And they did about 53.55 degrees, okay? I'm not sure they have enough legitimacy to that many digits, but that's what they get. How I knew that was fairly close to true is this is awfully close to 1 radian. So when you said 0.94 or something like that, that sounded right on the money. It's awfully close to 1 radian. The reason is, if this was 100 here, that would be 6 over 10, that would be 3/5, right? Yeah. And that's an angle that's pretty close, it's not exact, but pretty close to 1 radian. And so when you said 0.9 something, I thought, yeah, that's right on the money.
So what could I answer in degrees?
What's that?
So what could I answer in degrees?
Or radians, just indicate what you're doing, okay? Because most of the time in calculus they use radians, and for some reason this one they put the answer in degrees. Beats me of why. Okay. All right, I was trying to figure out what that next paragraph was saying, and I'm having trouble following it. This implies that the two planes have an angle of about 53.5 degrees or so. You can find the line of I misread. The line of intersection of the two planes by simultaneously solving the two linear equations representing the planes. Okay. And, okay. Now, I've drawn stuff all over the place. Let me go on and write down the answer. And for some reason, like you, I would have guessed it would be in radians. They did it in degrees. They said approximately equal to 53.55 degrees. I don't have a calculator up here, so I can do it. 53.55 degrees. Okay, that was their answer to that part. Now it says to find the line of intersection between the two planes. Okay? Now I'm going to erase some scratch work here that will probably be in our way if we were trying to actually solve this. So, okay. Here are our two equations. This equation and that equation. And we want to solve those simultaneously. And I think it's hopefully fairly obvious to you. You can't take them all the way down. You just don't have enough information to. But you can take it as far as you would like. Okay? It's not intuitively obvious that either one of these is that the line of intersection is going to be in one of the coordinate planes, if you understand what I mean by that, the xz plane, the yz plane, or the xy plane. Probably not going to be in any one of those. But what they suggest doing is solving this equation as far as you can. Okay? These two equations as far as you can. So I'm going to take out some more stuff because I do need more room to write. Okay? We got that answer. So let's take out this stuff. We already used this. We've already determined it. All right, goodness, I'm losing fast. I may have to head down to the office and get something to drink. I was hoping not to, but my word, I'm having so much trouble swallowing, and that is another thing. I ate my salad, but I really didn't drink anything, and that's probably also contributing to my dry throat. We really don't need the vectors anymore, just the equations, but I'll leave the vectors there. So x minus 2y plus z is equal to 0, and 2x plus 3y minus 2z is equal to 0. Okay, now, they chose to eliminate one variable, okay? And they chose to eliminate the x, okay? I find it easier to eliminate the z. So let's eliminate the z and see if we get the same result. So in other words, what I'm going to do is multiply the first equation by 2 and add it to the second equation, eliminating the z. They did this one by multiplying by minus 2 up here. Then you have to change signs. You might make a sign error. Really easy to do this. So let's multiply by 2. And that would be 2x minus 4y plus 2z equals 0. I just multiplied this one by times 2 and wrote it down here. Then add these together, you get 4x minus y is equal to 0. Okay? Which implies that y is equal to 4x. Okay. Now, and if you put this back in the original equations, you get x minus 8x plus z is equal to 0. And in the second equation, you get 2x plus 12z, plus 12x minus 2z is equal to 0. Okay? Now that second equation, forget that. Okay, these two become minus 7x plus z is equal to 0, and this one becomes 2x plus 10z is equal to 0. Okay? I'm sorry. Oh, is it? Oh, you're right, 14. I don't know what I was doing. Yeah, I added the wrong things. I can't read. You're right, that's 14x minus 2z. Okay. Like I said, my head is going crazy on me. 14x is won't write minus 2z is equal to 0. Okay, that will simplify to be 7x minus z is equal to 0, which gives you z is equal to 7x. Okay. Now they came up with where is it? Yeah, x equals z over 7. Okay. Now, the way I did it, we get x equal x, obviously, y is equal to 4x, and z is equal to 7x. Okay? So guess what? Let's just change the second x to a parameter. Now they happen to choose t. I thought they would. So rather than call it x, let's just call it t. So x equal t, y equal 4t, and z is equal to 7t. There's your parametric equations that will produce the direction numbers for the line of intersection. Okay? So in other words, and this is exactly what they got. They went a different way, but they got x equal t, y is equal to 4t, and z is equal to 7t. Okay? So plug in a simple number like 1, and you get 1, 4, 7. Those would be your direction numbers for the line of intersection. Okay? Now, then find parametric equation for the line of intersection. That's it. That's all we had to do. We didn't need this part. Those are your parametric equations for the line of intersection. And notice 0, 0, 0 is on it. Obviously, that both planes went through 0, 0, 0, and the line of intersection has to be on it. So that's all we needed. I don't know what exactly they were doing for the rest of it. And just a note at the bottom of the page, I was trying to figure out why they did this. Note that the direction numbers for example 4 can be obtained from the cross product. And didn't we do that originally? I don't know. The line of intersection of the two planes is parallel to the cross product of the normal vectors. Okay. That just was a note. You didn't have to do anything. I was trying to figure out why in the world they did that. All right. Sorry. That took too long. So let's move to sketching planes in space. This is so much fun, isn't it? Okay. All right, I think I can hang on long enough. I was going to say. My throat is so dry. I think I can endure. Okay, if a plane in space intersects one or of the coordinate planes, then the line of intersection is called a trace of the given plane in the coordinate plane. Wow. How many planes do they have in that sentence? Okay. To sketch a plane in space, it's helpful to find its points of intersection with the coordinate axes and the traces in the coordinate planes. And I think you'll see once you're doing this, they come out pretty directly and pretty straightforwardly. So let's see what we mean by that. Here's a plane. 3x plus 2y plus 4z is equal to 12. Remember when I said I like to write them in that form? Earlier they were saying 3x plus 2y plus 4z minus 12 is equal to 0. And I said, frankly, I like writing the constant on the other side. And that's exactly what they're doing now. Why they did it before, I'm not sure. So to find the xy trace, in other words, the place where this crosses the xy axis, okay, just set z is equal to 0. Because on the xy plane, I said axis plane, z is always equal to 0. That would be the floor down here. If that's x, that's y, and that's z, to find where that plane there crosses the xy plane, just set z equal to 0. There I did. And now you have 3x plus 2y is equal to 12. That wasn't that hard, was it? Okay? That line intersects the x-axis. Okay? Now how do you know that is a line now? And that's a line in the xy plane. Where does that intersect the x-axis? Okay? Well, where it intersects the x-axis, y's got to be 0, right? And 3x is equal to 12, so x is going to be 4. So it intersects the x-axis at 4, 0, 0. Where does it intersect the y-axis? X has got to be 0, y is equal to 6, so it's going to be at 0, 6, 0. Not too hard to do, is it? Okay? So now you have those 2 points where it crosses those two. If you want to go back and get the z, pick any of the other one, okay? You want to do xz plane or yz plane? I don't care. Pick one. Xz plane? So y equals to 0. And you have 3x plus 4y is equal to 12. That would be the line on there. And then set x equals 0 and you have z is equal to 3. So 0, 0, 3. There's your third point. Third point on a coordinate axis for that. Okay? And you go back and you got x equals 4 again. You could have done that, but we already knew that. Okay. So this figure 1149, which, yeah, is this one. This process is continued by finding the xz trace and the xy trace, and then shading the triangular region lying in the first octant. Okay? So, oh my. We determined 4, 0, 0, and 6, 0, 0, and we knew this line was this one 3x plus 2y is equal to 12. And z is equal to 0. All right. Now, using yz, and that's the one I think y'all chose too, we saw that yeah, z was equal to 3. So 0, 0, 3, I've forgotten what the number was. There's that one, and there's a line connecting those two. And then it's just a matter of drawing one more line from here, and there's a line that connects those two. So we did these. We did this xz trace, okay? But we still came up with z equals 3. So we did this one second, and that's the third one, okay? So this is 3x plus 2y. And these are really easy. You just take that original equation and this one, take z is equal to 0, that gives you that equation. This one, take x equals 0, you get that equation. This one, you get y is equal to 0, you get that equation. Okay? You get the 3 points, and there you have it. Now, I shaded in, that's the plane. It continues into other octants as well, okay? But this is just in the first octant. Now, a plane won't always be in the first octant. It could have been down here or over there or somewhere else, okay? this one, they chose something that would be in the first octave. All right. If an equation of a plane has a missing variable, such as 2x plus z is equal to 1, what does that tell you about the that plane? Well, it has no y dependence. So therefore, it is okay. 2x plus z is equal to 1. Okay. Obviously, there when z is equal to 0, x is equal to 1/2. So 1/2 0 is 0. And when x equals 0, z is equal to 1. So 0, 0, 1. Okay. Because there is no y in it. Okay. So here's your line that crosses here, but that line is everywhere. So that defines the plane here. So that's what it's saying. Then the plane must be parallel to the axis represented by the. It's a weird way to say it. The plane must be parallel to the axis represented by the missing variable. Okay? It's parallel to the y-axis. And that is just a strange way to say it. That the plane is parallel to the y-axis. In other words, y-axis never intersects it. Obviously, it doesn't. So, whatever that plane is that you have here, it goes like this, and the y-axis, it runs along the y-axis. It doesn't ever touch it, but it's always the same distance from it. Now, what bugs me about this illustration, and maybe it's just my imagination, but it looks like these two lines are getting closer together, and they should be staying. I guess they're not. I guess they're just the perspective of it is bad. Okay? So that's if you're missing an axis. I mean, missing a variable in the equation. All right. Now, if two variables are missing from an equation, then you have something, for instance, there's no y, there's no z in it, x is equal to something. Well, it's like ax plus d is equal to 0. So x is equal to minus d over a. And that's exactly what it is. It's a plane. Fine, come up. Now, this is assuming d is negative or a is negative. One of the two's got to be negative for this to be on the positive axis. If I were drawing this, I would have drawn it back here. Assuming a and d are both positive, this is a negative plane, one back here. But this is assuming one of those two is negative, and there's no reason to assume that. Okay? But if by plus d is equal to 0, then y is equal to minus d over b. Well, one of them must be 0 if that's positive here. I would have put it back here. Okay? And z plus d is equal to 0 is parallel. Do they just say here that d is negative? They should, to make this make sense. Then that would be up there. Yeah. For all three of these to make sense, d must be negative. They should have said that, but it's beside the point. That gives you, if you just have one variable in it, you're going to be a plane that is not dependent on that. Set that x, the one variable equal to whatever the other is. That gives you a point, and then the plane is parallel to the plane that doesn't have that variable in it, the yz plane, the xz plane, the xy plane. Wow. Now, distance between points, planes, and lines. Oh boy, what do we mean by that? How are we doing on time? We got a little bit of time. Let's consider two types of problems involving distances in space. Find the distance between a point and a plane. a line. Okay. The distance d between a point Q and a plane is the length of the shortest line segment connecting Q to the plane. Okay? So, here's the point Q, just somewhere out here in space. X, Y, Z component, somewhere out there in space. Here's a plane P down here. Okay? Plane P down there. Okay? Now we want the distance between the distance D between the point Q and that plane P. That would be the shortest distance, the perpendicular distance from this plane to that point Q. Okay? Now, and I'm trying to remember if we did these projections. I guess we did. Yeah, we did it with dot products. Okay, I believe we did. That D is the magnitude, because it's always positive, so it's got to be a magnitude of the projection of PQ onto the vector N. Okay? So basically, to make it a little simpler, you know this has to be a perpendicular distance. That's the shortest distance is the perpendicular distance. So therefore, you've got to have the normal vector. So it's going to be parallel to the normal vector, and you want the projection of that normal vector onto the point PQ. Okay? Okay. So the plane P, when you're given a plane P, remember it had two things. The normal components to it, you know, those were the direction things, and then your x1, y1, z1 were the points for P. Okay? So if you take that normal vector, project this onto the normal vector, that will give you the distance d. Okay? And that's a magnitude. Now, I'm trying my best to remember that we did that, and well, they're showing it to you now. For any point P on the plane, in the plane, you can find the distance by projecting the vector PQ onto the normal vector. The length of that projection is the desired distance. So here's how you do that. Distance between a plane and a point Q, not on the plane. Okay, obviously Q can't be on the plane. Then would be the magnitude of that projection. And what is that projection? The projection was the dot product between PQ and N. Okay. Go back to this picture here. The dot product between this vector and that vector. Okay. The dot product divided by the magnitude of N. Okay. Now, you have to take an absolute value of this because the distances are always positive. Magnitude is always going to be positive, so this, if it comes out negative, just do the positive. For P is a point on the plane, N is the normal to the plane, and Q is that point not on the plane. Okay. So let's see if we can actually do one of these. Well, not yet. Okay. Why not yet? Oh, I'm on the wrong page, that's why. Yeah, okay, here we are. To find a point in the plane, so here's the plane that's given to us. AX plus BY plus CZ plus D is equal to 0. Now they're going back to that form, where you put the D on this side. I don't care which side you put it, okay? Now, your assumption here is A can't be 0, okay? Find the point on the plane, AX plus BY plus CZ plus D equals 0, where A is not equal to 0. Okay? So as long as A is not 0, then set the Y and the Z both equal to 0. And then you get AX plus D equal to 0, X is equal to minus D over A. Now, there's a point on that plane, okay? If that plane just, if any one of those, if you have an X, Y, and Z in there, choose any one of them. If you're missing one of them, don't choose that one, okay? Choose one that's there, and then you can find the point that way. It's just set 2 equal to 0 and find the third, okay? Boy, they made it so complicated sounding, but that's what you do, okay? That gives you the point, and then from there, use the formula that we had here, okay? So now we're ready to do example 5. Find the distance between the point Q, 1, 5, negative 4, and the plane 3x minus y plus 2z is equal to 6. Now they've gone back and written it the way I like to write it, okay? Now, keep in mind, here's what you're gunning for. This thing right here. You're finding that distance, there's the formula. So let's go back and just write that down. That distance is equal to magnitude of your PQ dot N, PQ, that vector PQ, dotted with N, divided by the magnitude of N. That's all you have to do, okay? Now, how do you do that? First thing you got to do is find some point P that's on that plane, okay? Got to do that first, okay? Now, frankly, in my mind's eye, the easiest one to do would be let x be 0, z equals 0, and y is equal to negative 6. Won't that work? That works, obviously, okay? So here's a point that's on that plane, 0, negative 6, 0. You know that point is on the plane. It fits that equation, right? All right. Now, you need to do the vector P to Q. So this is your point P. So the vector PQ, that's easy to do, isn't it? Can you give it to me? P's in there. Say again. 1 minus 0. 5 minus a minus 6, which would be 11, right? Negative 4. Everybody see that? There's the vector PQ. Okay? Now, well, I said that. We also need that normal vector N. Can anyone tell me what that normal vector N is? It's 3, negative 1, 2. Yes, those are the coefficients of your variables there. That is your normal vector always. Okay? So now let's do a dot product between P and Q, PQ and N. And it doesn't matter which order you do, okay, because you're going to take absolute value anyway. It doesn't matter, okay. So I'm going to do N dot PQ because that's how it shows up on my page, and it's just easier to do. What would that be? 3 plus minus, minus what? Minus 11, is that what I heard? Okay. Minus, I'm sorry, a little louder. 8, minus 8. And that's equal to minus 19 plus 3 minus 16. Forget the minus sign, take the absolute value. So your distance is 16 divided by magnitude of N. Oh, how do we get that? Square root of? Second? 9 plus 1 plus 4. Square root of 14. There's the distance. Okay? Weird number, but okay, fine. No problem there. Okay? 16 over the square root of 14. Okay? And you can give an approximate value if you got a calculator and can do it. Okay? Find the distance, you did it. All right. You can then determine the distance between the point Q, yeah, okay, and the plane okay, and the plane AX plus BY plus CZ plus D is equal to 0. Okay. I can't for the life of me figure out why they're writing this again. I mean, it's the same formula as before. But there it is at the bottom. Well, oh, wait, I'm sorry. Let's go on and see how they did this one. Have we got time? Oh, we don't, do we? Okay, let's just see the answer that they do. Okay. All right, you know that is normal to the plane. To find the point, they chose 2, 0, 0. Notice we chose a different point. It's okay. All right, and they did that. And came up with the same answer we did, even though they chose a different point. Okay, y'all need me to go back through that more slowly? I just run out of time, so I was showing it to you. Okay. Now, they said that's about 4.28. Oh, here's the thing that they had at the bottom of the page. Let's just start there next time, okay? I just rushed through it. I didn't know that was on the slideshow. Okay. It's not going to be any clearer next time, but we'll do it. Okay. Sorry, we ran over a little bit. No